me run this. And let me show you the 3 blocks file. This is just modified from that hello.xml. All I do is I draw not one, but 3 boxes. You can see that there are 3 boxes, 1, 2, and 3. They're the same place, but they are put in different colors, red, green, blue. I'm going to use the first box rotated using Euler angles. Second one rotated using rotations. Third one I'll rotate using Quaternions. That's the plan. This code is going to take 2 start and end orientations. So I think it's here. So initially we start with 0, 0, 0, and then I'm going to try a bunch of final Euler angles. So first one is just rotate about x-axis by 90 degrees. Okay. Then we convert this to Quaternions, INF, rotation INF by using some of the utility functions. Don't worry about this too much, but essentially I will plot. I need to just modify. So what this code does is, for the Euler, it's just converts the Euler to Quaternions and then stores it in the Q pose, right? That's what you need to do. For the linear interpolation, I normalize it. I use that formula, linear interpolation formula, which is a function, which is kind of straightforward. Then I normalize it, and then I plot it. So this is 10 to 14 because remember there are 3 blocks. Each block is free. To describe the movement of any block, you need 6 numbers: position, velocity, position, and orientation. But because using Quaternions, that's what MuJoCo uses, you need 7 numbers. So you need 0, 1, 2 would be positions, 3, 4, 5, 6 would be Quaternions. That's for the first block. Second block, you'll have 7, 8, 9 would be positions, and 10, 11, 12, 13 would be Quaternions. So it just goes that way. So you have to keep keeping account of what that is. So here's 7 to 21. So 7 times 3, there are 21 degrees of freedom for this. And we are only interested in manipulating the orientation. Okay, so here is the Quaternion. I set it to the first block. I do the rotation. I do the interpolation. This is you see flatten. It's because rotation is taken as a 3 cross 3 matrix, and I want to convert that to a vector. And that's what this flatten would do. You can also do reshape. And once so this will be 3 by 3, but it's converted to 9 by 1. Then I do the linear interpolation, and then I reshape it to 3, 3. Okay, then I take the SVD, get rid of the S part, which I'm not going to care about. And if the determinant is -1, I just make one of those columns to be -1, and then that's my new R. And then I update my Q. And then finally, Quaternions. So looks like the third one is rotation matrix. First one is Euler angles, and the middle. Okay, so middle one is Quaternion. So you'll see 3. Let me run this. You'll see 3 things, but the middle one is Quaternion. Left one for you is Euler angles. Right one is rotation matrix. Okay, so that's rotation about one axis, x-axis, the red axis. Everything is okay because this is essentially a planar rotation. Okay, so this one is Quaternions. Left is Euler angles. Right, blue is rotation matrix. Let's go and change this to a different end Euler angle. So let's uncomment this one. So starting from 0, 0, 0, I go to change the pi by 2 and pi by 2 for 2 axes, x and z. Okay, so let's see what happens. See, all of them behave in the same way. Okay, so okay, now let's go to a third case where I have the third axis as 60 degrees. So you can see that the right one, the extreme right one, the blue one, behaved weirdly. We can run it again. So that's the rotation one. Let's run it again. Okay, so it goes slow and then goes very fast. So this is one of the problems with the rotation matrices, which if you rotation matrices, the time scaling will be messed up. Sometimes you can't say for sure without running the simulation. So because it's not specifically a property of what Euler F you use, it's really not a good idea to use rotation matrix because it will give you that weird time scaling effect. Now, yeah.
The first two are like still the same, right?
Yes, they work fine. Now we can take the fourth example, and this is going to be interesting because now I go through the singularity. Remember, the singularity for Euler angles 1 to 3 is when the middle one is 90 degrees. So I go from 0 to 180 plus 0.5. So the red one behaved weirdly. It ended in the same configuration, but it did go through a rather large rotation compared to the other two. So this one does not give the shortest path, and that's because it goes through the singularity. And clearly you can see that if you have a manipulator and end effector, you use Euler angles, it goes through the singularity, then it's going to rotate all over the place, which is not ideal. So this is just showing the issues with using these various Euler angles for interpolation.